Well, hello, friends. Thank you for joining us. This morning, I am so excited to have a speaker by the name of Dr. Daniel Corbett. And Daniel and I met through LinkedIn, and the beauty of LinkedIn is that we could see each other's backgrounds and credentials. In fact, I have it in front of me right now. I know, for example, that Daniel has a Ph.D. from the University of Washington, and he has a passion for science and technology. But interestingly enough, he also had a curiosity about business. And so instead of staying in the lab, he took a job with a company called CELLINK. And as I did research about CELLINK, what I discovered is that CELLINK was started by a young man who's 32 years of age, and it is a unicorn, meaning it is currently valued at $1 billion. And so that was very exciting. And so I'll tell you a fun and interesting story. As Daniel and I, over the last couple of weeks, we got together on Friday afternoon to prepare for this talk today. I was babysitting my 7-year-old granddaughter on Friday because my daughter Erin and her husband Nicholas are moving to Cape Cod, Massachusetts, arriving actually today. And so my granddaughter came in as Daniel and I are having a conversation, and I discovered that Daniel's mother is Chinese. And what you don't know is that my granddaughter's father, Nicholas, is Shung Jun Lee. And Nicholas and Erin met when Erin was teaching in China. She taught in China for 6 years. 4 of those years were in Shanghai, and 2 were in Sheko, just 45 minutes north of Hong Kong. She is an elementary school teacher, and Nicholas was a phys ed teacher. And so the two of them met, fell in love. And my granddaughter was actually born in Shanghai. And so I was so excited to introduce Mackenzie, or her Chinese name is Li Ko, to Daniel, because, well, I'll let you tell that story, Daniel. So I'll stop talking without further delay and introduce you to Dr. Daniel Corbett. Daniel, thanks for being here.
Thank you, John. Yeah, it's really a pleasure to be here at this platform with an opportunity to present on my past and current work. I could say that I love LinkedIn for being able to connect with people like John. In this brief amount of time that we've known each other, I could say that I've learned a lot from him, and he's really helped to accelerate. Coming from the lab, pure science. I need mentors and coaches, and more so, John's just been just a great guy to get to know. And so, the connection with his granddaughter, Li Ko, was certainly a fun connection we made. I know that she's a very curious child, where she was asking questions about roly-polies. And so I told her the scientific name of the roly-poly, which is the isopod. And she's just like, isopod. Oh, okay. Yeah, just, you could just feel it register in her head. And so very, very sharp, it seems like.
And she knew what an exoskeleton was.
That's right, yeah. And yeah, she was talking about exoskeletons as well. So a future biologist, it seems to be.
Fun.
And and I think that's a good lead in, because the company that get is a biotechnology company. And so it's, I think, if you sort of view the 20th century as kind of the age of computing and electronics, where personalized computing devices really came into age and fruition. I think a lot of people kind of view the same type of development in the 21st century for biology, biotechnology, and healthcare. So there's a lot of really exciting advances going on within these sectors. In terms of personalized medicine, analyzing genetic data, and the topic that I'll be discussing with you guys today, which is 3D bioprinting, artificial tissue fabrication. So hopefully that you guys will find this interesting and engaging. If you have any questions, please feel free to interrupt, and I'd be happy to answer. And hopefully we'll all learn a little bit about a really exciting new piece of technology throughout the course here. So I have some slides that I'll share. Activate that now. And hopefully you guys can see this. Can you see this okay?
We sure can. Looks great.
Perfect. Perfect. Yeah, so yeah, this is my company, CELLINK, the bioconvergence company. So this is a slide deck that I previously gave at a trade show presentation. So I think it's will also appeal to this group of individuals as well. And so yeah, so while this story it's a story about my company and what we do, but it's also a very personal story too, about how I came into this role. So the bioconvergence company, let's touch on that. So in terms of an agenda for this presentation, we first want to discuss what this term bioconvergence is, then go through the different ways of interpreting our name, CELLINK. It's kind of a fun story, and then open up for any questions. So before we go into the topic of bioconvergence, it's useful to know the motivators. So as mentioned, biotechnology is poised to explode, I say, in the coming decades, and partly because, definitely because there is a huge need for it. As you can see in this middle panel, on average, 20 patients die every day on the organ transplant waiting list. So these are patients who are waiting for a critical organ transplant, don't get one in time, and unfortunately they die as a result of their affliction. And this is really an underestimation, because these are just the patients who are on the list, right? It doesn't account for people who aren't registered, or people who a transplant isn't applicable for, who suffer from end-stage organ disease. And so I think we've probably all known someone who's been affected by some organ disease of some sort. And so it's represents a huge opportunity to try to address the loss of human life. And the ways that we are trying to address them are mainly through, or historically have primarily been through pharmaceutics, through drugs. And it's obviously, there's been huge accomplishments, achievements in that realm. But overall, I argue that the process is still broadly inefficient. So in general, the journey from a discovered compound, from the time of discovery to the time that it reaches market, can take up to 10 years. And oftentimes, drugs won't get disqualified from that process until the very end, until they've reached human trials. So they've already passed animal trials, they've sacrificed a lot of animals and spent a lot of money, and can waste up to $2 billion testing the wrong compound. So, this is an opportunity, right? This challenge of human health, organ disease, represents an opportunity. It represents both a challenge and an opportunity, and that if we're able to make progress towards these goals, the potential is immense. But we need to do this in an efficient manner. And this is where the phrase bioconvergence comes in. So if you go on our company's website, bioconvergence, or CELLINK.com, you will likely see CELLINK, the bioconvergence company. You'll see it pasted everywhere. And so what does it actually mean? And I think it's open for interpretation. So I've kind of taken some liberties to say what I think that it interprets, or what it means. And I think I draw this from a historical perspective, right? I think the idea behind this is that as a technology is allowed to develop, it will inevitably intersect towards the greatest problems, the greatest challenges that we face. And in the case here, this challenge represents human health or human organ disease, right? And so, we've seen this before, again, in the 20th century, right, with rises of separate fields like computing or genomics, or fundamental basic research like structural biology, right? As these fields have developed, for computing in the 1950s and 60s with development of the transistors, we've seen how it's intersected with the field of genomics. And then within the past 20 years, it spawned this new field of bioinformatics, of which now there are entire departments dedicated to this realm. Similarly, the intersection of all three of these, computing, structural bio, and genomics, have created this this field of protein engineering. So now, instead of having to rely on sort of natural compounds, penicillin derived as an example, that we need to rely on nature to create these compounds, and then we find them. We can actually start to engineer these, using the information that we've gathered and the technology that's developed from these separate fields. We can start to engineer new compounds that serve our final goal of addressing human health. And so similarly, the field I'll be talking about here of 3D bioprinting really came as an intersection of the biomaterials community with industrial additive manufacturing, so standard 3D printing, all toward this final goal of advanced tissue repair. So now I've given you a background on the problems that we face and sort of the philosophy behind it. How is my company, CELLINK, going about addressing this in a very specific way? And so in order to tell you that story, I want to talk about the 4 ways of interpreting our name, CELLINK. So the story begins when I was a graduate student at the University of Washington in a tissue engineering lab. And that's when I first came to hear about CELLINK. And I first heard about it through word of mouth. And so when I heard about it, first, I thought that the name read like CELLINK, as in links of a chain. And to me, that made a lot of sense at first time hearing, because again, I was in this field called tissue engineering. The idea that you can grow human tissues outside of the body and transplant them back into the body to perform a repair damaged or lost tissue. And so why CELLINK made sense to me was that, even though we've made a lot of advances in biology, most cell biology is done in this 2D cell culture system. So maybe a few of you have seen this before, but it's essentially cells are plated at the bottom of a dish, and then you add some liquid on top that serves as the cell's food, and that's how the cells grow. And there's a lot of problems with this, right? Because, when cells are in a single sheet on the bottom of a dish, they can't really communicate to other cells other than the ones that are directly around them in their circumference. That's not really how cells communicate when they're in our body, right? Cells exist within a 3D structure, and they're constantly probing their environment, communicating with one another, releasing signals. So altogether, this 2D format represents a really unnatural environment and is non-native. In contrast, native tissue, as I mentioned, is in 3 dimensions, right? Here we have things like mechanics, right? We have the stiffness of the tissue that varies throughout our body. Our bone is much stiffer than our skin, right? That when you're working in a 2D cell culture dish, you can't really replicate that. Moreover, we have cell-to-cell signaling. In a 2D cell culture dish, usually you're only limited to culturing or working with one cell type at a time. Whereas in a 3D system, you can start to integrate multiple cell types and moreover, position them specifically where they need to be to try to recreate the architecture that will foster the successful communication between individual cell compartments. Altogether, what this is establishing and what the field that I studied in of tissue engineering established over the past 20 years is that these 3D cell culture systems allow you to obtain more physiologic information about the tissue that you're studying. If you're trying to test drugs on tissue, you're going to get more accurate results in 3D. If you want to understand a tissue phenotype, you're going to understand it better if you work in 3D. And so the idea of cells linked within 3D, it made that there was a company that was going to be targeting this burgeoning area. In fact, I was wondering why it hadn't been done before. And then I saw CELLINK in print, and I discovered that it's actually the name as it is written, CELLINK. And so I think, for a lot of people that's confusing, but for me, it kind of had the opposite effect to where I became even more interested in the company because, even though because I was working in this field of tissue engineering, but more specifically, I was working around this technology of 3D bioprinting, right? And so this made sense to me and I would say it probably didn't make sense to most people. Because of this, the 3D bioprinting is still a niche community, but one that's growing very rapidly. So for those of you who are unfamiliar, 3D bioprinting is a process. It's a process that allows you to take a computational design, like this butterfly that I designed here in a software program, and then translate that into a series of instructions that a machine can interpret. And the machine can start to lay out the features that you designed. And it can do it all very rapidly in a very automated fashion, and to give you final constructs that combine multiple materials that are precisely positioned like you see here. And so we can see that, the ability to do this very rapidly, the ability to put things where they need to be, to separate things as according to a very precise software programming, is allowing bioprinting to erupt in pretty much the replication of any tissue. So if you go through the literature, you will see bioprinted version of bone, or bioprinted version of lung, blood vessel, heart, skin, kidney, everything. There's an analog for it now. And so, we're starting to actually see, for some tissues like the skin and cartilage, some of these bioprinted mimics are actually starting to make their way into the clinic. So, touching on that CELLINK, so why is it called CELLINK? Well, because in bioprinting, if we're using bioprinters, what are the materials that we use called? Well, they're called bioinks, right? This is a bioink cartridge. It's about the same price as a normal ink cartridge for reference. And so, the company CELLINK was really founded in 2016 by our CEO, Eric Gatenholm, first as a bioink company. What I'm showing here is pictures of our first bioink, the CELLINK standard. And what was really differentiated them, or what allowed them to sort of to come to market quickly, was the ability to use this ink as a sort of universal material. See, back when bioprinting was first beginning in 2015s or so, it was all very disjointed. So every lab had its own type of printer. They were using their own method. They were using their own materials, right? What our CEO came to realize was that there was an opportunity here to standardize this from different labs across the country by the materials, using this CELLINK material as the first universally standardizable bioink. So while we started as a bioink company, since then, we've moved into bioprinters, machines like you see here, or machines like what you see behind me, joining the two parts of this business in terms of giving, and essentially just trying to create an entire workflow for the researcher, from the materials to the equipment that's used to pattern the materials. And so we feel very well about our position in this industry, because the market research indicates that this market is expected to grow to $4.4 billion by 2028. That represents over a 50% increase from what it is right now. And so it seems like this technology is only poised to grow in the future. And so I just want to give you guys a couple of applications, or a couple of examples of how this technology is being used at the research level, by researchers. And so one of the first ones is this bioprinted skin graft, right? As I mentioned, skin is kind of the furthest along in terms of bioprinted tissues, mainly because it's a very simple tissue to replicate. It's very avascular, so it doesn't have blood vessels, or it has a few blood vessels, but it has relatively few compared to other tissues. And we'll touch more on that a little bit later. And so this was work that was demonstrated by our partners at Rensselaer Polytechnic Institute, Professor Karande. And in this work, what they did is they used one of our printing systems, and again, using the multi-material functionality of our printing system, they created two different bio-inks. So a purple ink and a red ink here. And so the purple ink contains one set of proteins and cells, keratinocytes and endothelial cells, I believe, while the red ink contained a fibroblast containing media. And they created this multi-layered skin structure of the two different cell types, 10 layers or so of the purple ink and then 2 of the red ink. And so what you can see here, first in images up top, you can see the different layers of how that's represented. Each one of these sort of fuzzy bright spots is an individual cell. And the fact that we have a green layer over on top of a red layer shows that they are creating this multi-layered cellular structure. What I think is really interesting also is that when you look at comparison of native human skin and you look at how it compares with the bioprinted skin, it's remarkably similar. In fact, the bioprinted skin seems better because it's a more ordered structure, as you can see here by this histological staining, and then also by the staining for various proteins of the skin is necessary to have. So it's filaggrin and CK14. You can see that sort of the ratio of this protein staining is similar in both the skin, in both the artificial and the natural skin, showing that it's a promising finding to show that we really are on our way to creating capable tissue mimics. And I want to give another example here in this emerging field of immuno-oncology. And so immuno-oncology is the idea that you can take your body's own immune cells to fight against cancer. Mainly this is for circulating cancers, so myelomas, lymphomas. And it's really representing a paradigm shift in how cancer is being treated. And so we wanted to know whether bioprinting could be used in an immuno-oncology model. Is there any space where bioprinting can serve a purpose here? And there certainly is. Touching on the advantage of bioprinting, the fact that it's able to do things so rapidly. So you can see here, this is one of our bioprinters, the BioX. And it's going through and it's just pipetting a single droplet on each one of these well dishes. And you can see that, it's doing it quite quickly. But the thing is that, this machine doesn't get tired. So it can pipette a droplet of this over and over, day in and day out, essentially giving you a very high throughput is the term, means of fabricating tissue models. And so what are the tissue models that it is fabricating? Well, they look like this. This is what's known as a cancer spheroid. So it's basically a ball of cancer cells clumped into a sphere. And as opposed to, cancer cells that are flat on a 2D dish, this sphere allows cancer cells to make connections with each other to start to deposit extracellular matrix is the term, basically a protein filling in between the cells that the cells use for support. And that really supports these cells and gives them a more native response to when we treat them with drugs or with cancer killing agents, such as the immune cells, which are known as T cells here. So in this diagram, you can see this is an individual well plate. So, you can imagine, this is like a well plate dish. So one of these wells, for example, right, has one of those droplets that I showed you on the previous slide, right? And those droplets, in each of these droplets are a collection of these spheroids. So that's represented by these red ellipses right here. So those are the tumor cells, right? And so in the media, the liquid food that surrounds these cancer cells, they incubate with the immune cells. And so what you would expect is if the immune cells are indeed killing the cancer cells, you would expect to see some kind of readout of cancer cell death, right? And so luckily here, the cancer cells are bright fluorescent red, so they give off their own signal. And so, we would expect that if the cancer cells are dying, we would see a decrease in the signal. And that is indeed what we see. So as we increase the concentration of the T cells in this dish, we see a decrease in the overall fluorescence or the signal of the cancer cells. You can see that here in this image, right? A cancer spheroid that doesn't have any T cells in it shines bright red, whereas a cancer cell that's been affected by the T cells is dim because of the cell killing effect. And so what this really represents is that you can start to use 3D bioprinting as a model to investigate immune therapies, right? We can start to modify these T cells in different ways and then start to compare how effective they are at killing different tumors. So it's a really exciting potential there. Finally, I just want to highlight just an actual example of our customers having success. And so the company that I've chosen here is this company called Ronak out of Olathe, Kansas. It's a two-person company run by the CEO, AJ Mellett, and the CSO, Heather Decker. And basically their idea is to use bioprinting to create this product called a T-block, or a tissue block, and to use these tissue blocks for the culture of stem cells. So as again, stem cells usually canonically when they've been cultured is in the bottom of a 2D dish. However, they had this idea that if we could culture stem cells in 3D, we could really improve the yield of stem cells, right? Because imagine, this 2D dish takes a lot of area, it takes a lot of space, and you're only able to get so many cells out of it. If you could move into 3D, not only could you achieve some of the biological benefits of having cells within 3D, but you could also achieve very practical benefits by reducing the amount of space that you need to culture these cells, increasing the density. And so, this T-block technology allows the stem cells to thrive in 3D. And in general, it gives a 30x yield of stem cells grown in 3D compared to 2D. And they recently received a COVID remediation grant. This is an old slide. So they also recently successfully had a successful round of Series A funding, raised $5 million. And so they're one of our top customers. They've been with us, known our CEO since the very beginning, and they seem very poised to continue on in the future using bioprinting as their technology platform. So, that's all of those examples represent how bioprinting and CELLINK are working in tandem to address outstanding problems within the fields of research and patient care. And then finally, the other way of CELLINK that I've come to understand is that we've gone beyond just the bioprinting industry, and essentially we want to become cell incorporated. And I think our strategy behind that is moving beyond bioprinting, as you see here, and moving more into the biosciences and the industrialization of biotechnology. And I think our leadership really identifies laboratory automation as being the key towards the industrialization. As I was working as a graduate student, there was a lot of things that could have been automated, I can say. There's you would spend hours just working at a fume culture hood, is what it's called, with your hands in the hood, moving liquids from one well to another, right? And it's important, and if you don't do that, then your experiments are going to fail. But it's not the work that I really think that scientists should have to do in the future, because we have bioprinters, the other technologies that we have the technology to automate these processes. And so CELLINK, what we've done is we've acquired different companies, Genolis, Maytech, just to name a couple, that are specializing in these other products and absorbing them as part of the CELLINK umbrella to sort of corner this market of generalized lab automation. And one example of that is the BioMDX, which is are going to be the largest bioprinting system to date. So most bioprinting systems, if you can see behind me, are kind of a desktop version. And so what we're trying here is with the trying to industrialize it by first building up the scale. Because, for example, if you're a company that has a vascular stent, for example, a small piece of tissue that you want to produce and bring to the market, you're not going to be able to do that on a small desktop printer. You need to start to have industrial equipment for this. And so this represents kind of the coming of age with the bioprinting. So you can see it has 6 different material tool heads here. It has individual cell dispensers too, so you can get really fine resolution work. and it's very high throughput. It can handle up to 27 microplates at a time, which is quite impressive. And additionally, it's in its entire own environment. So that should be coming in the summer. And so, yeah, that really is the end of my presentation here. I think, as John mentioned, I've moved from the science into business as a sales executive here with CELLINK. So that, should probably give you a hint to what the fourth interpretation of CELLINK is. But yeah, it's really been a fascinating journey for the first 5 months or so that I've been a part of it, and I've been able to meet really great people along the way, and sort of merge my scientific interests and passion with this business opportunity. And so I'm just really thankful for all of these opportunities, for the ability to work with CELLINK. The first thing that they teach us when we walk in the door is that we're always going to do right by the customer. And then I think that hasn't been refuted yet, and so that's good, and it gives me a lot of confidence working with this company moving forward. So that's all I have in terms of slides. What I would love to do now is take any questions on the presentation, and then move into an actual demonstration of the bioprinter.
Please, that'd be great.
If that's all right with you guys. Yeah. While you guys are thinking of questions, I'll just turn this thing on. Great. Okay. There's no questions. I'll just end then.
I'll have a ton of questions for you, but go ahead and Prit. I thought we were going to do questions after you demonstrate.
Yeah, we could do questions now, and then I'll move into, or if it makes sense, I'd be happy to take them after. Maybe after you guys actually see the machine in action, you guys will have more questions.
I think so, Daniel. Please.
Yeah, for sure. Great. This is a bioprinter. This is the CELLINK Bio-X, which is our flagship model, and it's really kind of the standard model of bioprinter around the world. This machine is in over 120 labs across the world, and I think it's been so successful compared to other bioprinters because of its user friendliness. So it really enables it so that you don't have to be a mechanical engineer, an electrical engineer in order to start to do this work. When I first started out doing bioprinting, I had to do a lot of programming and coding by hand, but now it's essentially all been very parallelized. So I'll take you through a couple of features of the machine. One of the things that you have to consider when you're working with cells is sterility, right? Your cells, when they're in an open environment, they're very prone to contamination. We're constantly shedding bacteria or other pathogens just from our own skin all the time. So, when you're working in a cell culture environment, you have to be very careful about where you move your hands, what you touch, and sanitize everything, right? So one of the things that, when you run bioprinting, your environment has to reflect that level of sterility. And so here you can see our printer is different in that many printers are completely open systems that you can, they're open to air and you can reach into them. Our printer is unique in the first sense that it has an environmental shield. So that's a very simple but important improvement. The other thing that the shield allows us to do is it allows you to filter the air. So you might be able to hear the fan running. And really what that fan is doing is it's purging air through two sterile filters that are coming through the top of the machine, creating a sterile environment and a downward air pressure flow as if you were working in a cell culture hood. So finally, and then the final piece of sterility that the machine has is, if you can see here, there's a logo that represents a UV disinfectant lamp. So there is a UV light on the inside of the machine that you can run, and UV kills it. So you would completely decontaminate the inside. So that's 1, 2, 3 ways of ensuring sterility in this system. So next I want to give you guys, so that's the exterior of the machine. I next want to give you guys a run through of the how to actually bioprint. So for that, I'm going to show you guys the interface here.
Yes.
So you can see here, it's very simple, right? There's only three options that you can choose from, right? So bioprint, droplet print, which I showed in the presentation, and then the select protocol version that allows you to sort of drop down and pick things, any protocol that you've saved before. So I'll first go to the bioprint option. Just let me plug in my USB here. And so when it plugs in, you'll see that it brings up a list of all of the different model files that I have loaded up onto my USB. I'll pick this one at the top here for the purpose of this demo. And you can see it's just a simple square that I can rotate within 3 dimensions here. It's pretty cool. And so what the onboard software on the machine does is it breaks it down. To actually translate this model into a physical 3D bioprint, it breaks it down for you step by step on the bottom row here, how that's actually done. So we'll walk through it here from left to right. The first thing it asks is, what surface are you printing on, right? Do you want me to print on a Petri dish? Do you want me to print over a 6-well plate, as you can see here, 6 different wells, so replicate the model. It has this glass side option. You can see that I have a Petri dish in there right now, so we'll leave that selected as it is. And move on to the next panel. And the next panel is where we actually select the materials that we're working with. So it's very handy here. As you can see, we have tool 1, tool 2, tool 3, and that corresponds to the 3 different tool heads that we have on the machine. And so just a word about the materials before I go further. The main difference between 3D printing, as it's commonly known as, and which I think many of you guys have probably had experience with before, the hard sort of plastic models that you see. The main difference between that type of 3D printing and this machine is in the materials that we are working with, right? We can't put our cells in hard plastic materials. We can't put our cells into 250-degree centigrade chambers if we want the cells to survive and study biology after, right? So what are the type of materials that we have to work with? Well, they're very soft, for one. They're mainly called hydrogels, and hydro being the prefix for water, of course, and our bodies being 70% water. These are mainly water swollen materials. So, if I, press down on this, this is just a syringe containing some of the material that we work with. If I press down, you can see it ooze out, kind of like toothpaste almost, right? And so in general, those are the type of materials that we're sort of, limited and forced to working with. Materials with that type of viscosity is what it's referred to as, the thickness of it. And so, the type of materials that have that viscosity that are useful for biology, that's an even smaller subset. And basically, those are proteins from the body, things like collagen, things like gelatin, for example, natural proteins and synthetic ones too, that we can modify, manufacture at a large enough scale and put them into our ink cartridges to start to do printing. So this is the type of material that we'll be printing today. And so if I go into here, I can select the individual tool heads, is what they're referred to as. And what happens here is if I click on the tool menu, and it's all touchscreen, I can bring up all of the different parameters that I'll need in order to run a bioprint, right? So things like, how thick is my nozzle diameter, right? That affects your resolution. What type of pressure do I need to push this syringe at to get the material to come out of the nozzle tip, right? How fast does the thing move? And it's all very simple. If I wanted to modify that, it's all very simple to do with this touchscreen. As a background, when I was coding these things by hand as an early graduate student, if I wanted to change something, I would have to, Control F and then find every instance of that parameter through this thousands of lines long code and change it all hand by hand individually. So now it's literally just a couple of button taps with your finger. So, excuse me. All of those parameters look okay. I think we'll move on to the next stage, which is the layers. This is where we actually get to visualize how our 3D bioprint is going to look like. So I'll click the preview button here, and what you'll see is this is our 2D square that I showed you at the beginning, parameterized into a 3D bioprint. So you can see it doesn't have the solid structure of the original 2D the square that I showed you, and that's because that's just a native property of 3D printing. It will automatically set this thing called the infill density to 25%, for example, right? That's something that we can change though, right? Again, right through the software program. You know, if I wanted to change that to something like 99.9%, we would see that we would get the completely solid square. So you know we have that capability. I'll change that back to 25 in the interest of saving both time and material. And then the other feature that I wanted to show you guys that I think is really cool is that, you know, this is interesting, this right angle sort of rectilinear pattern, but you know, we can do better. So the machine comes with a lot of presets of different patterns, things like a gyroid, this concentric-like pattern, which is useful for studying blood vessels, and honeycomb is my favorite. So we'll switch to that, and you can see, you know, it automatically updates with this different geometry. So it really allows users to experiment and play with different modes. And essentially, we're done. So that only took about 5 minutes, but we've generated a 3D printing protocol just by specifying the materials and the platform. And so all I really need to do is press print, do a quick calibration so that it understands where the zero surface, where the surface it's printing on is. And we can start you guys' first bioprint, I assume. I don't know if any of you guys have seen a bioprinter before. I'd be surprised. So this will just take a second. Okay, just took a second like that. And then I just need to prime the nozzle to make sure that the material comes out when we want it. Pressure a bit. Perfect. Great. All right. It's showtime. So let me turn on the light so it's a little bit easier for you to see. And we'll press start and watch our bioprint go. And there we are. Congratulations. You just completed your first bioprint.
Yeah. So Daniel, you did one of these before for me when you and I first met. Can you give an example of how that would be used in science?
Absolutely, yeah. So this was obviously a very basic example, but it does touch on sort of the key features of the machine that make it useful for scientists. One is the ability to go from a design to an actual model very quickly. You know, as when you're working in a lab, any second that you can spare, that you can cut off from lab time is extremely valuable. And so what this machine really does is it allows you to do that. Moreover, I mean, that's just a feature of the software and the machine itself, but the technology in itself too, the ability to actually create 3D structures using biomaterials, right? So, you know, in the field of tissue engineering, we are only interested in studying cells in their 3D context, in their tissue environment, right? You're not able to do that when you're working with petri dishes and well plates, right? So you need some kind of fabrication, some kind of 3D technology, right? There are other ways to do 3D technology, right? You can cast things in like an injection kind of molding apparatus, but there are a lot of problems with that. You know, you're limited in terms of the geometry that you can create, in terms of it's also a very laborious process. What 3D bioprinters do is that they really enable you to play with the geometry. So you saw that we were, you know, changing the different infill parameters. We had the different, you know, the honeycomb, the rectilinear, right? That geometry, you know, allows you to create different tissue types, right? And the tissue types that people are creating, as I mentioned in the presentation, are myriad. They range anywhere from the kidney to the liver to the heart. And it's really all based around the idea that if we can combine multiple cell types, right, and arrange them in geometrically defined patterns, then that gives us a handle. That gives us a toggle to, when we're studying biology, it's always a question of what do we have control over? Because biology is so complex and misunderstood. Sometimes, in our experiments in my lab, we were wondering whether the phase of the moon was affecting our experiments, right? There's just so much that's unknown, right? That we need to do our best with our technology to try to enable whatever level of control that we can have, right? And so the ability to control geometry, it's a very simple one, but it's also very salient in what it provides. And so what researchers are experimenting with is that they're combining different cell types, different types of materials, right? Arranging them in different ways to try to create more accurate representations of the tissue. So for example, liver tissue is an example of one, right? It's composed of multiple cell types that have a type of, I'll draw it out for you. It has this thing called a hexagonal structure.
Yeah.
So it has each of the livers is composed of these hexagonal subunits, and within these hexagonal subunits, there's a single vein known as the central vein, and at each one of the vertices of the liver structure, there's a portal triad, right? So there's an architecture to this, and it's not by accident either, right? The liver evolved this over millions of years because this type of architecture is crucial to the liver's function for detoxification, drug metabolism, all the 500 other things that the liver does, right? And so, having technology to be able to recreate that architecture, we can start to play with it, tune it, and evaluate it, see, if we do this, does it metabolize drugs better? Does it produce proteins better? And so it's really been a useful platform for those type of tissue models.
Great.
Yeah.
I wanted to say that I was excited to have you speak today for a variety of reasons. Earlier in the year, we had speakers that focused on our ability to communicate. And what this is about today, in my mind, is taking a complex subject and making it simple, digestible, easy to understand, because no one's going to make a purchase decision unless you do so, right?
Mm-hmm.
You also represent, through your educational and academic achievement, credibility with your clients, your prospective customers. And so that's a piece of it as well. So, and then finally, the reason I asked you to speak is because CELLINK, I think, as a unicorn with a 32-year-old founder, is an amazing case study for all of us to learn from. So, yeah, that was my thinking in inviting you today. And boy, you certainly haven't let me down. This has been fantastic.
Yeah.
Thank you.
Well, I have. If there's any other questions, I'd be happy to take them. But I also have a little bit more, touching on sort of kind of the state of the art research in this field, and where I kind of see where the field is headed right now. What are the major challenges?
Please, that would be great.
Great. And so this really goes back to my PhD work, and I want to first share my screen again, and then pose a question to you guys. Why don't we already have artificial organs, right? And sort of as a background in that question, I want to give you guys a video of this salamander, right? So, the salamander, you can see it starts here with its limb amputated, right? Over the course of a couple months, the limb is able to grow back. So we know that nature has the ability to create, bona fide regeneration, regrowth here, right? And we can study these processes, right? People have been doing so for a long time. So, what is the disconnect here between what we know about the salamander and what we can do in the lab? It's an open question. Do you guys have any ideas?
No.
I'll hit the obvious one first. One is we're not salamanders. But human biology is very different than salamander biology for sure. Does anybody offer any other ideas?
Jeff, please take.
Yeah, hi. I came in a little bit late on this. I think it's fascinating what you're doing. There was a news item out a day or two ago of a company, Nexa 3D, that raised like a ton of money for polymer 3D printing.
Absolutely.
Do you know anything about that, or how does that impact what you're doing?
Yeah, I haven't heard of the company Nexar, but it's essentially what what we are doing. So what I just demonstrated to you was an example of polymer 3D printing. It's the hydrogel. Sometimes they are referred to as polymers as well, depending on what you're working with. And so, yeah, essentially the polymers are useful materials, and that we can sort of engineer different parts to the polymer, that provide different functions. And overall, the idea of combining that chemical engineering with 3D printing, the ability to do 3D tissue structures, is really promising for the field of tissue regeneration. So yeah, Nexar, I'll have to look into them a bit more. But
yeah, it's Nexa 3D. It's a weird company name, but if not, let John know, and I'll send you a link.
Do you know where they're based out of?
I'm sorry?
Do you know where they're based out of? Are they American company?
No, I don't. John, we actually put out a news item on it a couple days ago. That's why I happen to know the company.
Great, Jeff.
Great. Yeah. So back
Could
to
I just ask one more question? I'm sorry to do this.
Yeah. Please do.
I always, when you look at something, I mean, you have a PhD, and this is really, state of the art, pretty advanced stuff you're doing. What is the commercialization, or is there a commercialization direction, or is this more for short, middle term, midterm, about just doing science to do science, which there's nothing wrong with?
It's definitely both, right? I come from, it's never just science to do science. If your science has to be funded by you have to convince someone essentially to part with resources to allow you to conduct this science, right? And so it has to serve some larger goal, right? And so there's different levels though that you can sort of drop off, right? So the ultimate goal is to be able to create artificial organs, right? I mean, I don't think I have to argue for the commercialization rationale for that. That if we had the ability to create artificial organs, I wouldn't have a problem selling them to you. I guarantee that. But we're not there yet, right? And so there's numerous, scientific sort of leaps that we need to hit along that way that before we reach that. And so in order to hit those, we need to have commercialization products, along the way towards that final goal. And so the commercialization projects that we're starting to see are starting at the very basic level, the equipment that you see behind me, right? So providing the users with the equipment so that they can start to experiment, do their own science, right? What we're also starting to see now is the development within both our business and within the industry is the development of 3D printed almost consumables, right? So instead of me giving you the printer, I can instead have the printer in my lab or my company, and then print out a mimic of liver tissue, for example, right? Like print out one of these things that I then ship to you, and then you can start to do your own sort of testing on it as well, right? If I print out a lot of them, I can ship them to a drug company, and they can start to their process testing as well. So this represents point of care models or personalized medicine. And overall, I think that's a one of the sort of the drop-off points of commercialization for this technology is creating these sort of on-demand tissue-based mimics that we can sell as consumables.
Hey, Daniel, I remember 7 or 8 years ago taking my team, we met here in Colorado on the Anschutz Medical Campus, and Jenna Hausman, the CEO of Children's Hospital Colorado, allowed us to use the Ben Nighthorse Campbell facility there. And when we toured the hospital, I was really surprised to see 3D printing of artificial limbs for children in the basement of that facility. Could you think of the printing of titanium limbs as an interim step, in a sense, for getting?
Absolutely.
Okay.
Yeah. And so most of my talk has been focused on the tissue element of it, but definitely, the prosthetic is a huge developing market for the 3D bioprinting industry, and mainly it's focused on the acellular components, so titanium alloys, a lot of electronics components as well. But yeah, this was 7 years ago. We were already seeing 3D printed prosthetic components, and the field, I think, has continued to evolve in terms of how well the prosthetics integrate with the person's own body, so their ability to do fine motor control. And so it's really exciting. I don't know of any companies, particularly specifically in the area, but I certainly envision that's going to be another strong area of commercialization for 3D bioprinting.
Do you imagine that CELLINK could be moving in this direction as well?
I don't foresee it in the future because the technology behind metal printing is very different than the type of 3D printers that we have. But our leadership is aggressive, and so I wouldn't rule it out.
Okay. Ben, did you have a question?
Yeah, I did. Can you hear me okay?
Yes.
Absolutely.
Okay. Yeah, I had a couple. One is around stability. What's the stability of the product? So you 3D print cellular material, or does it then regenerate like a normal cellular structure does in the body once the blood flow hits it, or how does all that work?
Yeah. That's a great question. Yeah. Stability is the post-printing process is what it's referred to as, is a very sort of nebulous region. And so it often depends on what type of tissue you're creating. Some tissues are going to be more stable long terms than other. But you're right in that the general idea is to try to get it to regenerate as it does in the normal body. So in the normal body, the cells will start to secrete proteins, secrete chemicals, that are vital for its function. We want to be able to do that with our 3D printed tissues as well, right? To be able to do that long term. But actually, one of the major challenges to that, and you mentioned blood flow, and so I'll just skip ahead a couple of slides here. Or actually, I can just point out to you right here, the vascular tissue challenge. Blood flow is a key, I think, attribute that has not been successfully replicated within 3D bioprinted tissues yet. One that is very vital for the tissue long-term stability and function, but it's been very challenging to actually implement at a practical level. So in general, generally our users will experiment after they bioprinted tissue. They'll run experiments on them within a span of 2 weeks to a month. Sometimes longer if they're depending on. But I think in the end goal, the idea is that you'll print the tissue, go through a short phase of sort of maturation, and then immediately implant it into the body, into which it will have the body's natural cues and retain it and to grow in the body.
Wow. Okay. And then when I was back not long ago, a while ago, we were doing work for the Navy on manufacturing parts, which is not biology, but you would basically get a broken something and you would 3D render it and download it to a CNC machine or a 3D printer, and it would generate a new version. What's the process flow? So if I say, eventually we're going to go to an artificial organ, do I need a sample from the person to get the DNA match, so it's not rejected? Do I have a schematic for a generic heart, and I modify that for the person? How do you envision, if it's not done now, how does that work? I mean, I'm in a hospital, So like when we were doing it for the Navy, the submarine would submit an order. The Navy would pull up whatever drawings they have or a broken part, we'd get it, and then we'd make a new one and send it out. So we had we basically get something, create a 3D map of it, put that map into computer numeric code so the machine would know what to do, and then proofread the code, make sure it was right, put the right material in the machine, hit the button, and 9 times out of 10 you get a new part, and the 10th time you get a really loud bang. I demonstrated the really loud bang once. One wrong piece of code was very expensive. But anyway, so yeah, how does that work?
I think it will look pretty much the same. I think that process has been tried and shown to be successful. I think it will probably be the same type of process with some variation adaptations to make it biological, right? But I mean, the beauty of 3D printing is that you can customize things to individual patients, right? Because the machine, it's not limited to a single mold, right? As an injection molded thing, right? It builds everything from scratch, right? And so what a lot of people are doing with the 3D printing is they are using patient scans, right? Imaging data from MRI, CT scans that can be digitalized, turned into code, just as you were doing with the submarine parts, and then fed into a 3D printer. So you could have, as you suggest, you could either have a template or you could take patient scans and modify directly like that. But the flexibility to do this all sort of computationally is really what's powerful with 3D printing and additive manufacturing. And then from there, the other adaptations, once you have the model file that you want to create, I think this actually touches on one of the challenges of why we don't have artificial organs, right? Is we don't have it is that you need to actually fill it with cells, right? So the idea of proper cells, right? How do we avoid immune rejection, right? If you could use the patient's own cells, well, we know that those are tolerated by the patient. That would be great, right? And there's ways to do that now with stem cell technology. However, the problem with that is that it's hard to grow up the number of cells. So that example that I showed you of Ronak before, right? They're targeting this need, the inefficiencies of current cell growth production, trying to increase the yield so that we can, when time is right, we will have enough of a patient's cells to actually 3D print their structure. And then, the other one is the actually trying to assemble cells into the tissue. So tissue is a remarkably complex structure. I think, the resolution is going to be very different when you're working with biology, when you're working with mechanical parts like submarines, right? Generally, you have tolerances on the order of millimeters or inches. I would am I accurate in that?
Yeah, they get down tighter than millimeters, but yeah, you get down to hundreds of millimeters. But it is interesting because the thing about the work we did for the Navy was you had to make a custom part every time. Right. These weren't, we had a general idea of what the part might do or be, but we had to get direct measurements because unfortunately they don't maybe fortunately, they don't mass produce submarines. And some of the ships and some of the surface ships were World War II ships. And so there weren't even any drawings. A lot of those things were battle repaired, and the guy would send us a Polaroid photo of something and say, I need this. I need something to fill this hole. And we're like, yeah, okay, sure. But and then worse, they couldn't, in a lot of cases, tell us anything about it because it's classified or above my classification. So I couldn't, it's not like, oh yeah, I've seen that before. But so in the cellular world, because what jumped to mind is there's a lot of interesting discussions in sports medicine about these meshes they're using instead of plates and bolts to repair sports injuries. And apparently they're growing them, not 3D printing them, which not quite sure. I mean, the guy explained it twice, but still, I'm not quite sure I understand how you they grow a mesh. He said it's really like a Band-Aid. It's like a big bandage. And they have a standard for different parts of the body because, sports, you get the same injuries kind of repetitively. And then they can surgically implant these meshes and they're good for life.
That's really interesting.
They don't, it's not like a metal implant where you have a foreign body in the body. So I'm just trying to connect those thoughts of saying, well, yeah, you can make anything. And there's this whole science around growing meshes, and then this science around 3D printing.
Assembling them, yeah.
Yeah. I mean, maybe they go together. You do some things as a grown mesh, and then you assemble 3D printed parts on top of it. I don't know. I mean, that's asking the question.
Definitely, yeah. I think it's a great question. I would be interested to learn more about the meshes because, I mean, presumably if they're growing, there's some biological component to it, right?
Right. Yeah. They do them in some kind of science-y environment that doctors would understand, and us engineers, if it doesn't smell like oil, it must not work.
Yeah, right. That's interesting. Yeah, so I'd be curious to know, like, what the biological component is that's feeding this growth, and then if they're not using 3D printing, then the growth is kind of just happening, and I said randomly, right, just sort of ballooning out. Which might be useful for their purpose, but I would argue that there's a lot of data that shows that the structure of the mesh, right, has an impact on how the tissue is going to interact with it.
They're using a trellis. They're using a trellis. They grow it on something and then separate it.
I see. They grow it on a substrate. That's interesting.
Yeah, that's substrate. Thank you. Yeah, that's the official word. Right. Yeah.
Yeah. That's I see. Yeah. So that's definitely a method that's being explored, right? I think one of the limitations there is that it's still kind of a cast removal process,
right?
So it's not really personalized to a patient, and then it's hard to actually do a larger 3D structures there because you're limited to the thickness of whatever you're working with.
Right. And
so yeah,
it's not an organ. It's not an organ replacement. It's more of a steel plate replacement for sports injuries.
Yeah.
I think they've got a kind of it's like replacing a flat tire. There's a very narrow variation of what you need. And so you can produce the bandage or where in your case, the good thing is they can pre-grow them where you actually have to do all the measurements first.
Right.
So
right.
What you're doing what you're doing is very, very different.
Yeah. And then, but it fits under the same ideology where I feel like, in the past, we're starting to see that, it's now more economic to just replace than it is to repair, right? If you imagine if you have like a plumbing issue, right, you can spend a lot of time, trying to diagnose it, calling a plumber, but, ultimately you probably just need to get a new pipe or something. And so, for a long time, medicine has been practiced under this repair strategy, right? Like what drugs can we fit to try to recover any kind of lost tissue function. But now with this, cellular technology, with the ability to, personalized designs and measurements, grow things outside the body, we're starting to reach the stage where even at the biological scale, this replacement ideology is starting to take hold.
Right. So that makes sense. And the precision of the machine must be very, very high to.
Yeah.
Actually, I meant to ask that is if you're laying down a 3D cellular structure, is precision a critical element, or can it just grow, fix itself?
Absolutely, 100% precision is a vital factor, and actually, I'll touch on this in the next slides here. So, there's a difference in bioprinting methods, right? And the major difference in the methods are in the level of precision that they supply. So, what I just demonstrated to you was an example of what's known as extrusion bioprinting. And it's extrusion because the material is coming out of a syringe here. So you can see here's the cellular material, with high cells and hydrogel. It's loaded into the syringe, and then the syringe comes down and ejects it out, right? what's the, what level of precision do you think you can get using this method, right? If you had to put out like what's the smallest diameter thread that you think we can print?
Have to be in the thousands of millimeters. It'd be very small.
Right. Yeah. So it's even smaller than that. So it's 150 microns is general is the limit of resolution. So that's um, yeah, 150 microns. It's like 10 widths of a human hair. Right. But what's the diameter of a cell? Well, the diameter of a cell is about 10 microns. So, is it sufficient to have this type of patterning resolution to where you can only pattern about 10 cells or so at a time? And some people argue no. Some people say that we need to get down to single cell level precision, because that is the scale at which biology operates at. And so to that effect, there's a lot of research going into what's known as light-based 3D bioprinting. So this is based off of the same technology that was foundational for the electronics industry, or the rise, the ability to pattern high density number of transistors and integrated circuits on silicon wafers. It's the same technology, right? Basically what, it's just, if you're familiar with it, this will be a review, but what happens basically is that you use light from a projection system, and this light is patterned through the use of these really tiny mirrors on the inside of the device. So you can control basically individual pixels, whether they're in an on or off state. And you shine this light on a liquid. And what the liquid does is it hardens basically where you shine light off of. So here's an example of a liquid that we use for this type of 3D bioprinting, right? And I'll play this video again. Basically what happens is that by shining different photo masks, so different sort of, you can imagine them almost as PowerPoint slides, it cycles through these PowerPoint slides, and while it's doing that, it's building up this 3D structure. So you can see areas that are white are receiving light and hardening, where areas that are dark are hollow because they don't receive any light. And so then this is an example of how it actually looks like in practice, right? We're pulling this object from a vat. And so because we're working with light, the technology working with light that's been foundational for our electronics has a remarkably higher resolution, right? We can get down to nanometer scale precision when we're patterning electronics, right? So there's a lot of potential here if we can start to transfer this to the biological materials, right? And so this was work that I was actually part of as a graduate student, where we use this technology to create hollow channels within these 3D structures, trying to replicate actual blood vessels, one of the major challenges that I mentioned earlier, right? And so you can see here, trying to replicate, this level of complexity, this 3D level of, the way that these vessels, intertwine and move in 3D, it would be impossible to do using the extrusion-based method. Only with using light can we actually start to replicate, these type of models. This is an example of a lung model that we have, where we have an interior air sac surrounded by this fluid structure on the outside. And what we showed in this work was that as you ventilate this air sac, you are actually inducing mixing of the blood in the channels. And you can see here, or you can see at this juncture here. And so, so not only is this foundational technology, does it have potential, but it already is starting to realize that potential in terms of discovering mechanisms for biology that we could only study by having this high resolution fabrication capabilities. So, this was my PhD work, and it was done. I'm going to stop sharing here. It was done using this machine right here. And so, I'm sorry. I realized we have Jeff. We have a hand up. Please, Jeff. Do you have a question? Perhaps he's away at his screen.
I'm sorry, who were you asking about a question?
Your hand.
Oh, you.
Yeah, I don't have any others right now.
Okay.
So, I mean, I just wanted to demonstrate, I have a couple of those things that I just showed you here. We can actually take that liquid material and turn it into a solid, as I can show you here. If any of you guys have kids, perhaps you'll recognize this character.
Oh yeah.
Right? And so you can see, the finish, it's so smooth.
Yeah. Yeah, that is a great way to demonstrate precision.
Right. Right. And then I have an actual model file here. So, this looks like a plain block of hydrogel at the onset. And if you just give me a second, I'll demonstrate that it indeed has interesting structure to it. I was originally thinking that I was going to switch to a phone view for this demonstration, but I think I can demonstrate it for you guys manually right here.
You know what, Daniel, while you're preparing that, I just wanted to say that it always amazes me how different parts of our federal government, whether it be the DoD or in this case NASA, has an interest, for example, in tissue regeneration or curing cancer. And it just comes from different places that to me seem unexpected.
Absolutely, yeah. I think there's many different routes to this ultimate goal of health and human hair. So here, I'll just want to show you guys this example real quick. Hopefully, I can push it.
So you're filling.
Wow.
Okay. Yeah.
Right.
Look at that.
So you can see, we can start to create, tissues. You can put cells inside this, and we can actually start to feed them with blood now. We can actually start to actively, perfuse them. And so, using this machine, this creating something like this would be super hard to do. So it's really only through light-based 3D bioprinting that technology is possible. And I think that's kind of where the field is heading and where the opportunities are in improving the resolution and cellular level scale. Really excited because CELLINK actually. So this machine, there's a little bit of background that I made those constructs on. I worked on this as a graduate student when it was still a beta version. So I worked directly with the inventors of this machine. They since commercialized their technology into a company called Volumetric. And so when I was graduating my Ph.D. and it was time for me to find a job, it was a very easy transition for me to come to CELLINK and say, hey, I've worked on this machine before. I know what it's about, and I know that I can sell it. And so that's essentially what led to my position here. And so that's an overview of light-based 3D printing, a demo of what I have, and I'd be happy to take any other questions. I have about 20 minutes left. I can show the TikToks as well. What do you think, John?
Sure.
Just before we do that, can you talk a little about muscle? When you
Yeah,
show the idea of something moving, like that lung, that's done by electro energy in a muscle, causing the muscle to move back and forth. That's not as easy as some organs, the static organs might be.
Absolutely.
So how would that go about?
Yeah. So I think it also touches on like the post-printing process that we're talking about. So generally, we do have users who are printing muscle, both skeletal and cardiac, right? And generally the way it does is that you'll combine the cells into our syringes, into the printer. You'll print out the tissue model when it's still static. And then in the maturation process, in the post-printing process, that's when the cells will start to connect with each other, and then it'll start beating. So at first it'll start with very small twitches, right? And then it'll get stronger and stronger as the tissue matures. Some interesting work on that is the ability to actually measure the muscle force of your printed tissue. So you can print the tissue and you can print it directly on two like pillars, right? Your vertical pillars, right? And so you can imagine the tissue is what bridges this gap between the two pillars, right? And these pillars are connected to sensors, right? So as the muscle contracts, right, it pulls on the pillar. And as the pillar pulls, you can start to calculate by how much that pillar deflects what the force of the muscle is. So you can start to actually, develop relationships, right? Understand, we have this metric for evaluating our muscle tissues with bioprinting with sensors. What type of drugs affect muscle readout, what type of different materials and combinations of materials affect the muscle behavior. It's really interesting work and great question. Thanks for asking.
Sorry, John, go ahead. Thank you, Daniel. That was great. Thanks.
Mm-hmm. Jeff, how about you? Any final questions? Daniel, I want to end with a big thank you. Mission accomplished today. You are.
Well, is he doing the TikTok video, John, or did we skip that?
Yeah, it'll only take a second, and I just wanted to, I guess, thanks, Ben. Yeah, and thank you, John. Just because you connected me with Nate and other people from sort of the educational sector. Yeah. I just also kind of want to touch on the, the educational values of these machines. They're very.
Because Rick Russin, who's building a STEM program at Valor Christian High School, could not attend this morning because of finals, but. This recording will enable him to see this today.
Absolutely.
Are you implying you can 3D print a lecture of some form?
Well, the lecture could be about.
Because I could use when I was a lecturer, I could use it. I could have had a stand-in. Go ahead.
Yeah. It makes the jobs as a teacher a lot easier.
Yeah, you were saying the lecture could be about, sorry, I interrupted.
The lecture could be about 3D printing because, what are the skills that you require to be a 3D printer, right? A 3D bioprinter. Well, you have to have a fundamental knowledge of biology, materials, how they interact. You have to be able to program a little bit. You have to know a little bit about electronics. You have to know about 3D modeling, especially, right? And, these are all, valuable, hard STEM skills that, we try to educate through labs and lectures and stuff. But it's obvious. I think a lot of research shows that, if you have fun with what you're learning, you're going to retain it more, right? And so that, 3D bioprinting really offers a really useful tool, for students to get excited about education. And so, I demonstrated that, I think, in some TikToks videos that I've made, trying to, reach a younger base and get engagement here. So, I'll just show it on my phone and bring it up to the screen for you guys. This is a bioprinted taco.
Very good.
So Daniel, do you know how many views you got with this?
Yeah, don't tell them.
I had this one, not too many, but I did have a bioprinted pizza that right here that got 25,000 plays on TikTok. And the same process here. So you can see.
Yeah, I definitely want to share this with
sauce in the pizza.
Yeah.
Yeah. So those are just fun little demonstrations, but they also show how different bioprinting ways can work together, how to work with machines, instrumentation, and so that's as at CELLINK, that's an area that we're targeting, and I'm personally trying to take a lead on is the educational route that these machines can play, or the roles that they can play.
We did not share that your father is an academic and that his area of expertise is history, and I can see that in you, the educator in you, Daniel.
Yeah, it definitely comes from my dad, and Richard Feynman, who was the subject of this meeting's packet, has always been a personal role model of mine. Luckily there's a lot of videos of him on YouTube, so that I was able to really, take in his words and his wisdom, after he passed. But yeah, my dad is an educator. I used to sit in on his classes as a kid. As we have a Richard Feynman. You have his book. Is that a biography? Or you're muted?
It's not a no, I had only one hand. This is his actual lectures. Someone found this for me. It's the CDs of his recordings of lectures, and they're there we go, and they're moved to CDs.
Wow.
So you can listen to them, and then it has the lecture notes that go with it, which I don't understand. He's trying to prove some orbital. He wants to do something. He's trying to prove orbital dynamics with graphics instead of math. And he says these were lectures he did just for fun, and he's got the old style Caltech whiteboards that go floor to ceiling that you slide up and down. It's fabulous. Some of it's video and some of it's audio only. Some of it is clearly recorded by a student in the back of the room. You can hear the pencil,
Yeah.
Feynman's
Wow.
great. If you could find this around if you ever wanted to do it. This was a gift, but you must have bought it from somewhere.
Yeah.
So
Yeah,
it's called the Feynman's Lost Lecture. And there's a couple of them around. And then he got me some other ones because he knew people at Caltech.
Wow.
So, that they just burned them to CDs. So, they're not, I don't have copies of those, but yeah, he had a great sense of humor. He was a great communicator of incredibly complicated things, and a safe cracker and a musician. So he was an excellent drummer.
Renaissance. I did not know that about him, actually.
Oh yeah, he was a drummer and a safecracker. So if you forgot your combination at Los Alamos, they'd get Fineman to come in, and he would come around and open people's safes for them. And it's funny because it was not to spend too much time, but it's prescient of today. He said 9 times out of 10, he could open the safe by dialing the default combination the manufacturer put in it. So the password was password.
Yeah.
Never changed.
Yeah.
Some things never top secret safes in Los Alamos, and you could open it with the manufacturer's default combination. Well, what can you say? Yeah, if you're a buff of he's written several books that are just wonderful reads. But the lectures are really quite interesting. But anyway, it was really good to talk to you, and amazing the work you're doing. Do you have a time frame? So I know why NASA's interested. NASA's the progenitor of almost everything that happens in the hospital now. If you have a cardiac arrest, your life is safe because NASA did the work. All the heart monitoring stuff, and they did it because they had to teach what they used to call dumb astronauts how to restart a heart. They had to know when the heart stopped and when to get the astronaut to start it. And they have to do it in a way that an astronaut trained to fly a fighter jet can. And so all this technology, so I could see immediately why they'd say, if we're going to do trips to Mars, we can't send a spare organ for every person. So we have to, and they're working, some of the friends of mine in manufacturing doing the same thing with 3D printing. They're trying to figure out how you can manufacture basically a spacecraft out of something where every individual part could be 3D manufactured on Mars. So whatever breaks, you just make a new one.
Exactly.
What do you think the time frame is on this?
Well, I think we're still a far ways. It's hard to project with accelerating returns. But for reference, so that vascular tissue challenge that I referenced in the slides. So basically, that's NASA's challenge to create a 1 centimeter thick tissue that is perfusible, that has a competent blood system, and the award for that is I think $5,000, and no one's claimed it yet. So I mean, obviously 1 centimeter is marginal in terms of what the size of a liver is, right? So it just represents how strict of a barrier this vascular problem really is, and so I think we're still probably 10, 20 years away, which honestly isn't that long, but 20 years probably from starting to see solid organs getting 3D bioprinted solid organs making their way to the clinic.
And when you were doing your PhD research, did you see opportunities for things like artificial and augmented intelligence to speed the research, or is it really hardcore grunt work because there just isn't data sets to teach computers?
Yeah, I think that's right on point. So right now it is a lot of working with your hands, right? There's and that was kind of like the basis for the foundation of our company, was that all these people were kind of working on their own little islands. We needed to standardize this if we're going to move this along faster, right? And so it still is very much at that level. Anytime where you have to actually work in the physical world, right? The machines are less adept, right? What we are seeing though in terms of AI and machine learning is in the computational design, right? So being able to mathematically generate a lot of different of optimal designs, for example, of if you give it a certain set of parameters, like I want to maximize oxygen diffusion, right? You can develop a program that would be able to do that for a given tissue or a given model. So that is really useful, and I think an emerging area. But down the road, as we start to generate more data sets and sensors within the system, we'll start to get more computational methods will become more. They'll move further down the process and further along the pipeline.
Wow. Okay. Wow, that's amazing.
Yeah,
that's amazing.
Daniel, I know you've got a hard stop here in a few minutes. Again, I'm so grateful for your participation today.
The pleasure is all mine. Thank you. I've had so much fun to talking to you guys and learning about all of your experiences as well.
So you and I'll regroup sometime later. And so thank you for being here. Do you have any final comments you want to make before I stop the recording?
Just to reiterate my thanks. Thank you, John, for providing me this platform, this opportunity to present this, what I think is really interesting, fascinating work to you all. And I'm glad you guys have taken an interest. And please do, connect with me on LinkedIn. I think you have my email. Please let's stay in touch. I think that business is all about in science. You find a lot of people who are working on the same project. And you go for that. In business, it seems like you want to get as much diversity in terms of thought patterns and processes as possible. So I really encourage continued communication between all of us, because we do come from very different backgrounds, have very different priorities, but we do all have very similar goals, it seems like.
I can promise you that. Thank you, Daniel. Have a wonderful day.
Thank you very much.
Talk to you soon.
You guys have a great day as well. Thank you guys. Bye.